Hello, everyone. This is Scott, your instructor and lover of hash browns. Today, we're going to finish up our conversation on hash tables and specifically get into what happens when we have collisions. We briefly talked about this last time, but then also how do we actually do this in practice? And that's going to lead into your next project. So just as a very quick review, I want to skim over this. I don't want to spend too much time on it. The whole reason we're doing this hashing process is so that we can get to element access of O1, of constant time element access. Now, this asterisk is here because at the end of today, you're going to see that it's complicated. It's not nearly as clean as, let's say, like a binary search tree, which is always log 2 of n as long as it's a balanced binary search tree. So that's our motivation. That's what we're doing. Our hash goals, which I just want to redefine. Remember, guys, hashtag goals. It's like a meme, but it's also a hash because we're doing hash functions. It's not Octothorpe goals. It's hashtag goals. Anyway, explaining jokes makes them funnier. Didn't you know that? Our hashtag goals here is that our associative container is going to give us fast access. The kind of downside, the thing we're giving up, is that we don't care about the order. We don't care about finding the thing next to an item. All we care about is finding an item. And we also are sacrificing any semblance of efficient memory storage. That's going out the window. So those are our goals. Just in the back of your mind, that's what we're dealing with. The goal here is that we are having a fixed size table. So what that means is we are defining what our table size is ahead of time. This is before we have put any data inside of it. And then we're using some kind of hash function to figure out the mapping from a key to a element location, to a index in our table. So in this example, we have Finn. Our hash function is giving us the value 4. That gets us to entering Finn in a specific location in our array. Okay, again, as just a recap, when we're talking about good hashing algorithms, we want to make them diverse. If we were to take a whole bunch of names and then just use the ASCII value of their first letter of the first name, we're going to get a pretty terrible distribution. Notice that all of these indices are not being used, and even the upper indices aren't being used. We only have 26 different spots to put things in data. Now, that's not great because we're wasting a bunch of space. So instead, we can do more complicated hashing algorithms, which will give us more diverse and more separated, more disparate hashed key outputs. So in this case, we then sum up all of the ASCII values of a name. That's going to give us a little bit more spread, but we still see that there are some voids, right? There's not many names now that are falling within this 51 to 71 range. We're getting a bunch of things in the 1 to 21 and a bunch of things in that like 86 to 100 level. So this isn't great. We want it to be flat, right? This is going to get us towards why we were talking about adding up with powers of 31. Again, 31 was kind of arbitrary. You could do a 31. You could do it with a different prime. You could do it with some other method. But we're trying to get a nice even hash function. And I bet that if we were to expand this index from 100 to 200, this would even out even more. Some of these spikes might be because we're compressing things so much in this space. Okay. The goal here, again, goals, our hash function is going to spread out those key pairs evenly. We want the results of our hashing function to be as varied as the potential unique inputs are. Then the other thing is that we need those hash functions to be efficient to compute. It doesn't make any sense if our hash functions take a long time to compute, because that's the whole point. We want it to be quick. We want it to be efficient. That gets us down to that more constant time. Okay, so let's get into collisions and how we can deal with them. This is kind of the nitty-gritty of the downside of hashing. So let's to simplify, instead of doing this whole like 31 power prime addition thing, we're instead going to use a very basic hash function for the majority of this conversation. And what we're going to say that our hash function is that we're going to have the index value be equal to the length of the name. So Finn would give us a index value of 4, Ray would give us an index value of 3, Chewbacca would give us an index value of 9. Straightforward. The goal here is that we want to be able to do this quickly, but there's a potential problem So what's the problem? Well, it turns out that Star Wars has a bunch of names that are all like 3, 4, and 5 letters long. So Kylo, Solo, Luke. If we get into the 5 letters, we're going to get Vader, right? We're getting a bunch of names that are very similar lengths. So they're not unique. That's the problem with our hashing function. And we talked about last time that one thing that we could do is we could make our hashing function more efficient. But then the other thing we can do is we can deal with the collisions. So let's look at an example really quick of a very basic hash table. We have it sized 7. So that's fixed. That doesn't ever change. It has a size of 7. And then we insert into it Finn. Okay, great. Or in this case, we want to find it, right? I'm looking for Finn. Our hash function is going to get us to the index 4. That gets us to the entry of our key and our data. That works. That's fine. Now, our collision happens not here. Sorry, I'm getting ahead of myself. This isn't going to form a collision because Ray gives us a unique key value that's going to get to a unique different array position. Now, what happens if we try to pass in something that has a larger index value than our array? Well, the standard thing to do is to just modulo the number. So in this case, we're going to take 9 modulus 7, which gets us to 2. This is essentially wrapping around. If we think about 6, 7, 8, 9, that puts Chewbacca just in a wrapped around fashion. Okay, that's nice. That solves that kind of short-term problem. But here's our issue. What happens if we try to now insert Kylo into our hash table? Well, Kylo is going to result in a hash key of 4, or a hash value of 4, which means it's going to try to go into this array location. But the problem is that array location already has an entry, Finn. Okay, this is where we can come up with some strategies. But to be very specific, when I talk about a collision, what I'm talking about is that we have some hash function with some key giving us the same answer as some different key with the same hash function. So this is unavoidable. We can try to make them unique. We can try to make them different. We can try to make a lot of room in our hash table. But ultimately, there's a possibility that we could have our hash functions equal the same location, which is an issue. There's a bunch of different things. We're going to cover 3 of these today. There's a whole book, honestly, probably a whole course that you can get into on just different ways that you can deal with this. We're just going to lightly cover 3 different strategies: linear probing, chaining, and then cuckoo hashing. Cuckoo hashing is just great. Again, there are lots of ways to do this. So let's start with linear probing. The basic idea here is that the hash value is just simply a hint. It's a suggestion. It's a kind of, hey, it's over there hand wave kind of action. So what's going to happen is when you convert Kylo into the hash value 4, we're then going to go look at the value 4. But if this is not Kylo, which it's not, it's just going to skip to the next one. So we just skip one spot and we put Kylo in the next location. Okay, that's decent. That's fine. The next time I come and look for Kylo, I'm going to go to 4. I'm going to then look at Finn. That's not Kylo. I'm going to go to 5. Oh, that is Kylo. Great. I found what I'm looking for. Now the problem becomes, okay, what happens if we try to pass in Luke? Luke is going to have an issue. It's going to go to 4. It sees that Finn is there. It's going to go to Kylo. It sees that Kylo's in there. Well, it just goes one more and it puts Luke in. Okay, that's fine. Right? If we want to access any of them, Finn, Kylo, or Luke, we're essentially going to go to 4 because they all are going to give us the same hash key or hash value. And that hash value is going to result in finding this location and then simply step through them. So they all kind of coexist at 4, but they're also pointing at 5 and 6, which leads to some issues. Okay, so one of the issues is going to be what happens if we get something like Lando that has a 5 value, right? 5, Lando, Lando, is going to get our hash value of 5, but Kylo is there, so now it's going to go to Luke. Luke is there, it's going to wrap around and go to 0 and put Lando there. Okay, that's okay. Dengar, same thing, 6 letters. It's going to go into Luke. It's going to step forward and step in. So that's going to lead to a potential problem, and hopefully you see there's a pattern that's emerging. What's the worst case access for a linear probing hash table? we can see right now that if our hash function, let's say worst case, gives us the same hash value every time, that means essentially we're just doing a linear search. And a linear search is ON, which is exactly the opposite of what we're trying to do, right? We're trying to get as far away from ON as possible. Okay, so that's not great. That turns out that linear probing is okay if we increase the occupancy ratio. And what I mean by that is if we increase the size compared to the number of elements in our hash table, we can kind of deal with that. We can certainly reduce the likelihood, the probability of collisions happening, which then makes linear probing okay, right? Sure, it's going to be ON kind of, but it's really only going to be ON as some like scalar from the occupancy table, right? So there are some ways that we can manage that. It's still going to be smaller than true ON, but it's still not going to be great. Okay, what are some other issues with this? Well, what happens if we remove fin? Right, I insert fin into my hash table, I do some stuff, I do some operations, I eventually want to remove fin for whatever reason, and I go to remove. So I pass fin into my hash function, that's 4. I'm able to find the entry for fin right away. I get to its entry at 4, and then I delete fin because I don't need it anymore. So I delete fin. The issue is going to be what happens when I go to look for Luke, right? We have disjoint probing. If I go to add Luke, my hash function is going to convert Luke into 4, and then it's going to go to the 4 location, and it's going to say, hey, great, I don't have to do any probing because there's an open spot here. I can put Luke right there. So as soon as we do that, all of a sudden now we have 2 different locations for Luke. And if we ever go to search for Luke, we're only going to search for, the first one, right? We're only going to see the Luke that we entered at the 4 location. Now, again, this doesn't matter if these 4211 stay constant, but that's not a guarantee. That's kind of defeats the purpose of our container. What happens if that's a full class and it has more complicated methods and elements inside of it? Okay, so that's going to be an issue. We got to deal with that in some way. And one of the strategies here is that we can put in some token that represents that, hey, something was deleted here. There used to be something here, but now there is no longer something here, right? We're going to add this delete token that suggests to the container that, oh, well, in the future, if I'm looking for Luke, instead of saying, hey, I didn't find Luke because the 4 is empty, I'm instead going to look here and say, oh, we've deleted an object here, so Luke may or may not be linearly forward, right? I keep going forward. I'm going to go to Kylo. Nope, that's not Luke. I go forward 1. I find Luke eventually. Now, one of the other things that can be helpful here is that if, for example, Lando didn't exist and this was just blank, eventually, if I'm looking for, what's another 4 named Yoda, right? Yoda would come in here, find delete. No. Kylo, no. Luke, no. Lando, well, I said I deleted it. So it's going to look at the 0 and it's going to see a delete. And then we go 1 more and it sees just a null space. And so it says, oh no, Yoda doesn't exist. I've exhausted all of the possibilities of Yoda. It does not exist. It's not there. I can pass back. Nope, not found. Okay. So linear probing, pretty basic, pretty straightforward. The idea is you go and you just keep stepping forward in your array until you find an empty spot. You do have to deal with this issue on deletion, but that's okay. So what are our potential fixes for this problem? Well, we already kind of talked about one. We could certainly make a larger table. This increases the amount of voids in our space. That means that we'll have less collisions because we just have more spaces, right? If you think about, if everyone walked outside of their house right now, you're probably not going to collide with someone else. But if we make the population density a lot tighter, then you probably are going to run into people, right? So the whole idea here is that if we make that occupancy smaller, then we increase collisions. If we make that occupancy bigger, then it's going to allow for less collisions. All right, so the other thing we can do is we can get better hash functions. That's always going to be helpful for us. If we make a really large data with a really solid hash function, we're definitely going to have more spread out data. And this comes back to these graphs, right? These graphs are not arbitrary. I actually generated these graphs based on the same information that you grabbed the the names from the exam. Those are Social Security Bureau like name lists for the past couple of years. Well, the past hundreds of years. I think you can pull from 1800s. Anyway, the point being that like these are real representative names, and what I was doing was I was running our hashing functions and then just recording the indices for each of the names. Again, the whole point being that if we can move from even a hash function like this into a hash function like this, we're going to get much better spreading and much less collisions. Now, again, even in this example, there's only 100 possible locations, which means that by definition, we're trying to enter 2,000 things into this table. By definition, we're going to run into a problem because the guaranteed 101st item is going to collide no matter what. And in fact, in this instance, you're gonna collide and then just keep looping infinitely because you're never going to find an insertion point. That's going to be solved later on with chaining, right? Chaining is going to kind of solve that problem of having a small occupancy space. All right, but there's one more thing we can do in our in our linear probing is we can use quadratic probing. So linear probing is using a +1 modifier. So every time you go to look at something and it doesn't exist, or there's no space, you then add a +1, you step forward in your array. Quadratic probing is you're going to use this pattern of some index squared, and that's going to allow you to then step further in memory, which means that you essentially are forced to avoid clumping, right? The idea here is that the Finn Kylo Luke blocks Lando. That's a problem with linear probing, but if we do this quadratic probing, we're kind of getting these arbitrary spaces between the hash place we're looking and then the hash place of the next duplicate item. This just helps you spread out things and again avoid that potentially problematic clumping issue where everything kind of just like groups together, because when you enter Lando then has nowhere to go and then Lando gets stuck. Quadratic is going to allow you to quickly spread out into the rest of your table. Again, this is highly dependent on even like what kind of data your key is, what your hash function is doing. It has a lot of implications on kind of the context of your hash table. All right, so the second strategy is chaining. Chaining is essentially going to make our array not so array-like, but instead have our array be linked lists. So every element in our array really is just a pointer to a node, and then that node is then going to hold a pair. And so this is kind of like in a weird way, kind of like a dequeue in that we're having this kind of structure over our structure, and this is going to allow us to do some pretty intuitive elements. So in this case, if we have a collision, if I try to enter Kylo into my hash, I'm going to go to the fourth location, and instead of having to do this linear detection, which is we go down one, instead we're going to go here and see, our 4 hash value has a thing in it already. It already has an entry of Finn. So I'm just going to push onto the back of that list, and I'm just going to push a new node Kylo. That's nice, right? That means that I'm only ever going to have to deal with collisions for things that map to that one hash value. So in this case, 4. So now when we go to Lando is going to get its own entry because there wasn't anything at the 5th hash value. If we keep going, we add a Luke. We're just going to keep adding to the end of that list. Now, what's nice here is that if you ever need to remove something from a specific location, if I need to remove, let's say, Kylo from my 4th place, I'm going to go to my 4th hash location, and then I just step through until I find Kylo, and I do a linked list operation of removing a node, which then has Finn pointing to Luke, and there we go. Okay, so what's the worst case here? Well, it turns out the worst case is still ON, right? What happens if our hash function gives us back the same value every time? If our hash value or our hash function is still biased towards single values, then that means that we're essentially just going to get a giant linked list, and we're just back to linked list searching. Not great. Okay, so the nice thing is that we don't block other hash values. That's nice, that's good. But we are still at ON. So this gets into the same thing of how do we fix this issue? How do we get back to OC? Well, we can certainly have larger tables. That's kind of going to help us. That's only going to help us in the case of the modulo operator, right? If we get a hash value that we then have to modulo and loop around, that modulo then overlaps with a different hash value, right? That's going to be where we get kind of compounding collisions. So a larger table would help with that. And certainly a better hash function would help with that as well. But that's also, notice, the same benefits or the same potential fixes to the linear probing problem as well. All right, so the third kind of method we're going to use, or the third strategy we're going to use, is called cuckoo hashing. So for this, we're going to use two different and distinct hash functions. So when we detect a collision with our first hash function, so in this case, Kylo is going to detect that it collides with Finn. Then we're going to pass Finn into a new hash function. In this case, I'm going to have it be the first letter of the ASCII, or the first ASCII value of the string, instead of just being the length of the string. So we're going to convert Finn into a hash value. This hash value is going to come out as 6. That 6 then is going to be the new location of Finn. We copy Finn down into 6. And now there is no collision for Kylo. We can then put Kylo in at 4. Okay, that's nice. The reverse is going to be the same thing. If I pass in Finn and I get Finn at 4, and then I go to my fourth location and I look here and I say, hey, hold up, Kylo is not Finn, then I'm going to pass Finn into my secondary hash function. That secondary hash function will then get me down to 6. Okay, that's nice. Now, why would we move Finn and not just move Kylo down? It's an interesting question. This is largely related to the idea of temporal association. And what I mean by temporal is like time. It's time association. Most of the time, this is on average, you are more likely to interact with the thing that you have just pushed into a data object, into a data structure. You're more likely to. That's not a guarantee, certainly. In the case of like a stack, that's the opposite. Well, no, I shouldn't say it. No, a stack is temporally associated, whereas a queue is directly opposite. The thing that you pushed in most farthest away is the thing that you're getting back. But this is just a rough strategy of like, hey, if we're going to have to make a choice, we might as well make this choice that is somewhat intuitively developed, right? That we want to move the thing that we haven't touched most recently, because the thing that we are inserting is the thing that we are touching right now. So what's the issue here? Ooh, well, it's not great if we have another collision on 4, because what happens if I try to push Luke into the fourth location? Well, then we're going to pass Luke into hash function 2, but then what happens if hash function 2 pushes Luke back onto Finn and then we get a collision there? What do we do next? Do we have a third hash function? Well, right, this is where it gets just complicated, right? If you get a double collision, things are just real bad. And so it turns out that if you get consistent double collisions or triple or quadruple collisions, you're going to get a worst case, which is ON, right? You're seeing a pattern emerge here, which is that most of the edge cases of worst case scenarios for hash tables are going to be ON, which is just not great. So this gets into this whole idea of our implications for our hash tables. This is the kind of crux of this whole lecture. The perfect complexity, the perfect ideal hash table that is going to be able to have perfect hash functions that give us entirely unique hash values, and we have infinite space, so we have no collisions, right? That will get us to OC. This is for an ideal hash function. The problem, though, is that as soon as we start putting caveats onto these perfect things, as soon as we, in the physics world, as soon as we start making things not round spheres, as soon as we start making things more real, all of a sudden it gets more complicated. So as soon as we start introducing lower quality hash functions, we're going to be moving towards an ON kind of operation. As soon as we start restricting the amount of space we have, we start pushing towards ON operations, right? All of these things are going to be pushing us back towards ON complexity. And this leads to this idea that like the reason we don't always want to use hash tables is because sometimes we shouldn't. Yes, OC is much, much better than ON. However, it's at the expense of a couple things. One is our space efficiency, right? Efficient tables don't have anything in them. and empty tables are wasted space, right? These are two sides of the same the same kind of idea. So that's going to be an issue. And then the other thing too is that creating unique key values is not necessarily straightforward, and it's not necessarily guaranteed either. And so it's a little complicated how we want to do that hashing. Now, there are some general hashing that you can do based on like the binariness of whatever the type is. But still, that's going to lead to complexities in that, some things might still hash very close to each other. You still might have deeper problems. So the whole point here, this is like the underlying thing I want you to pull out of all of this hash table idea, is that what we are doing is we are trading efficiency for access. No, I shouldn't say that. We're trading space for access efficiency. We are trading these kind of caveats that are going to be not great, but in return, we're getting extremely good efficiency, again, if used correctly. Part of the reason we've waited so long to introduce hash tables is because in the case of like a vector, it's very straightforward what the efficient things are and what the inefficient things are. When we get to a list, same thing. The things that are efficient are pretty standard. The things that are inefficient are pretty inefficient. In the context of a hash table, efficiency is a lot more complicated to grapple with, right? Now you guys all have a really good mental model of what these efficiency scales look like. So now we can have this more deep, in-depth conversation in terms of how the hash table works. But again, underlying point, hash tables sacrificing space for efficiency. If you think about like a vector, that's almost as space efficient as you can get. It only holds the data, but that's at the expense of both the finding efficiency, but then also the replacing efficiency, the inserting and removal of a item from a vector that comes at a cost. Okay, that's enough jabbering. Let's get into the implementation. How do we actually do this in our code? Well, on Wednesday, someone asked me a question about the STL library and if it included a hash table, and I said no, it didn't. I forgot about this one thing. Right, the set and map, the underlying structure for those standard template library data structures are going to be binary search trees. In C++ 11, which, not to date myself, was after I graduated from college, C++ 11 introduced two new containers, the unordered set and the unordered map. These two things were hash tables with linear probing. And so they work in very similar ways in the context of the methods that are available to you are similar. However, they're going to be implemented differently in the unordered set. You don't have access to an iterator. You don't have access to things like that allow you to get into your data. But unordered set, unordered map, they are going to give you hash-like operations. Okay, so also, if you're in other languages, Java has essentially hash tables with hash sets and hash maps. Python defaults to having hashed sets and hashed dictionaries. I just want to give you guys a heads up in terms of standard libraries in different languages. So yes, they exist, they work. The problem though is that if you're considering a hash container, then you have to define that hashing function, and that gets a little complicated in C++. It gets complicated in Java and Python too, but it's a little weird to be passing around function pointers and stuff like that. So that's why it's different and weird and new. Okay, so for our implementation, I'm just going to jump straight into Project 6 and talk about what you are going to be required to do. You are going to implement a hash table, and you are going to implement that hash table using chaining. So this leads to a question of, okay, well, where do we start, right? If we're going to be doing chaining, this is the idea that each hash index is going to be mapped to a linked list. We can utilize two things we already know. We can utilize a standard list, and we can utilize a standard vector. You are more than welcome to use your lists and vectors from Project 2. You don't have to, though. You're welcome to just use the standard template library. So we're going to have some vector in some list, and then we're going to have some hash function that will then allow us to access our vector, but then that vector is going to be of a list, and so then that list you'll be able to push things onto. If that seems weird to you, think about it, it's actually not too complicated. This project is going to allow you to lean pretty heavily into the standard template libraries of both vector and list, and it shouldn't be too bad. It shouldn't be too complicated. I don't want to get into passing around function pointers. There's a lot of stuff that happens there that I just don't want to deal with. I've made it an extra credit portion of the assignment. It's just a whole nother kind of sub thing you need to learn, and so that's why I'm going to avoid it. And what we're going to do is we're going to use a standard pair. I gave you a pair that you can use. If you want to write your own, you can. But the pair is going to be a string with then some type. So you're going to have some string as your key and then some type being whatever you want to contain inside of your hash with that key. That does need to be templated, but the string does not. You always can use the string. Now, as a heads up, just because some people might ask about it, there is a function called rehash. This is up to you to implement. I'm not really going to cover too much of it, but the basic idea here is that when we get to a certain occupancy level, we can choose to just rehash. We can take the both memory and processing hit to make our hash table bigger and then reinsert all of our items. And that reinsert will then hopefully spread things out a little bit more. It's called a rehash. Just if you go to implement it, you're welcome to. I'm not requiring you to do it, but you're welcome to. Okay, so what you're going to do is you're going to implement a hash table that implements or that holds pairs of string and type. Again, I've given you this, so you're more than welcome to use that. If you want to replace it, you can as well. You're going to have to make an insert method. This is going to be essentially finding where the pair that you are trying to insert, where it would go inside of your first vector. And then if there is a thing at that vector, then pop or push onto the back of that list. If there's not a thing, then you need to make a new linked list. You're going to need to make a removal method. You actually need two of them. One is going to pass in a whole pair with both a string and a type. That's going to have you go and find where that string is and then deal with removing it. There's also a method that will allow you to just pass in the key by itself. You don't have to pass in any type with it. You can imagine those are going to work the exact same way. They should probably call one another, or right, one should call the other. That'd be the easiest way to do that. You also need to create a locate method. Locate is going to go find the internal object that you're holding. You'll see here that locate is going to return back an iterator. To make this project a little bit more palatable for you, you are more than welcome to use the iterator of a list. It's going to break down our idea of our hash table kind of contract in its interfaces. However, I'm okay with you leaning into that as an easier way to implement the iterator, as opposed to writing your own iterator and then implementing that. If you just pass back the iterator of the list, all we're really using the iterator for is to be able to access the element and manipulate it. So for example, if we're doing this mailbox example, I'd want to look up by name, and then I might want to get some piece of information from that type that then allows me via the iterator to then access the data inside of the type. Again, you can use the list iterator, you can use your own iterator. I don't really care, it's up to you. One of them is certainly easier than the other. Okay, that's about it. We got two homework questions that are getting at kind of some things that happen with hash tables. This also concludes, as kind of a side note, this concludes our conversation around containers. The rest of the class is going to be focused on sorting. We're going to spend, I think, 4 lectures on sorting, which is a whole different beast. You're mentally prepared for it, that your kind of mental context is going to be well suited for it. But we're stepping away from containers and moving into sorting. Someone was asking me questions about due dates on this stuff, and it's getting a little hairy. That's fine. I just want to give you a heads up that we have an Excel sheet in our Blackboard page that has lists of the rest of the semester. I would refer to that. This project I'm going to assign currently as I'm pushing this out. It's going to be due next Friday, which is the 1st. There is no second part. It's a single part project. It's also only worth 50 points. It's worth half of a normal project. I don't expect it to take you too long. I also want you to be a little careful of your time management, because I'm going to assign the sorting project, which is project 7, on Monday, and it will be due the week after. So you'll have things due both this next Friday and the Friday after. And then we're also going to get into exam 4 and the final project. So just be aware of your time management. these next couple of projects aren't as stringent. I know that you've already done a lot of work on the previous 5 projects. These ones aren't as bad, or hopefully not as bad. Okay, cool. Bring questions to the conversation on Friday. We'll see you there.